Having seen the description of two dimensional spectrum, please recollect that a random wave can be described in the frequency domain as a function of, and this is how it is represented. So on the y axis is nothing but half into amplitude spectrum. So the area under this spectrum gives you the significant wave height or the total energy contained in the C wave. This we have already done and we know what it means. This means that waves are travelling in one direction. This is true if you are generating a random wave in a wave flume, that is in the laboratory. But this is not true in the case of open ocean. In the open ocean, if you consider the waves propagating from the deep waters, and if you consider a shoreline, somewhere in the deep waters you have the waves generated because of the blow of the wind blowing over the water surface, and the waves are generated somewhere here, wherein the wind will be blowing in different directions, so the waves also will be propagating in different directions. And when they propagate towards the shore, as you all know, that it undergoes the phenomena of refraction, so which means that this will orient itself more or less parallel to the bottom depth contours. So as the waves from deep water propagates, its direction gets aligned parallel to the bottom depth contours, and somewhere near the coastal waters more or less your direction is well defined. That is, you can say that here the waves are more or less coming in almost a particular direction, but in deep waters you cannot say that, rather questionable. So this essentially means that the waves in deep waters will be coming from different directions, and hence just mentioning about S of eta f or describing the wave profile in terms of only f is rather questionable. So in deep water you should have another function, that is the distribution of the energy or the waves coming from different directions have to be considered. So this will be represented as f comma theta. You see the difference between S of eta, S of f and S of f comma theta. So this is referred to as a two dimensional spectrum, and this is three dimensional spectrum. So we call 2D waves and 3D waves. 2D waves, their representation as a form in the form of a spectrum, it is termed as 2D spectrum, and 3D waves, that is waves from different directions, when they are represented in the form of energy distribution, it has to be associated with direction also, in addition to frequency as described in the 2D spectrum. So that is the basic difference between 2D spectrum and 3D waves or 3D spectrum. So representation of sea surface wave spectral functions against wave frequency, that is the wave spectrum. Directional wave spectrum, the concept of directional spectrum is introduced to describe the state of superposed directional components, that is waves from different directions. So hence there should be a way of obtaining this. How do you obtain that? By equation 1, that is you simply multiply the 2D spectrum, which already we have seen under random waves, by a directional spread. That is how the energy can be distributed, how the distribution of the energy in terms of direction can be described. So that is obtained by d of f comma theta, that is directional distribution as a function of frequency and theta. Is that clear? So now later we will see, as we have seen here, there are some standard spectra like Breshenet spectra, John Swab spectra, Pearson-Moskowitz spectra, Scott spectra, so many spectra are there. And we have also seen the usefulness of looking at presentation and which can follow some kind of standard distributions. In a similar way, we also have some standard distribution for directional spread. So if you want to simulate 2D waves in the lab, you can simulate maybe a Pearson-Moskowitz spectrum. You want to simulate, you know that in the field, the waves in the field maybe of Chennai, you have waves following, say for example Scott spectrum. Then I want to simulate the same kind of waves in the lab, and there is a situation that there is not much of a directional spread. Then I will resort to test in the tank, in the flume, that is capable of generating the wave elevation that will simulate the waves which will follow the Scott spectrum. Okay. For that matter, any spectrum can be included. This mainly is nothing but sending the signal to your wave maker and dictating how it has to move. Okay. So you will generate a predefined spectral characteristics, but the same way you can also generate a directional spectrum, wherein if you have already proved or someone says or you yourself want to test, you can select a particular 2D spectrum and an associated directional spread. The associated directional spread, it can be a measured spread which can be obtained by doing some measurements and followed by analysis. You can arrive at the directional spread, or you can use a theoretical directional spread and test your structures how it can function, or numerically also it can be done. So basically what we are trying to look at is how do you represent the distribution, the simulation of waves, how do you represent the wave elevation. Before going into that, this is how the distribution would look like. The top figure shows the distribution of energy. If you take one single wave, spectrum, say this can be as a function of frequency for a particular direction or vice versa, On the y axis it will be the energy or of amplitude square, which is nothing referred to as spectral density. So if you superpose all these things, then you get a 3-dimensional view, and that 3-dimensional view is called as the directional spectrum. Is that clear? So you will have long expressions, but I will just show some of these expressions, and the only thing is, after having a look at the lecture, patiently go through all the equations and try to understand. So although I have discussed something, some few points, I have listed here the directional wave spectrum. Surface spectral density function is proportional to the energy of waves. Hence, directional spectrum gives energy of the waves per unit plane area against different frequencies as well as directions. I explained that. That is the volume represented by S of f comma theta into df elemental frequency and elemental theta directional is now proportional to the average wave energy per unit horizontal area, and the variables are mentioned there: frequency, bandwidth, d theta is incremental of directions, and S of theta is known as the directional spectral density function or directional wave spectrum, spreading function, angular spreading function or directional distribution. So you have a number of names assigned to S of theta. Now the directional spreading function carries no dimension and is normalized by, as shown in equation 2. S of theta is equal to S of f into d of f comma theta. So d of f comma theta, that is, as I have written here earlier, so this directional spreading function carries no dimension and is normalized as shown here. Is that clear? Now as I mentioned earlier, why do we have to, I have already mentioned earlier, why do we have to look at the method of representing the surface elevation or the surface wave profile? Only then you will be able to describe the wave characteristics. So there are several, there are broadly 2 methods or more than 2 methods, but broadly classified it is classified as single summation model and double summation model. What we are looking at is a double summation model, wherein you have a double summation. One is n equal to 1 to infinity, and the next one is m is equal to 1 to infinity. Note that on the right hand side you have the amplitude A of m comma n associated with both direction and frequency. N stands for the number of directional components. How many directions are you going to include in your simulation? And m represents the frequency components. So you have Km is nothing but wave number for that frequency component. You have to, K is nothing but, you already know K is 2 pi by L, and L is going to be a function of frequency. So naturally you will have to calculate your K, and now t is the time and then epsilon n is the random phase angle distributed uniformly between 0 to 2 pi, which I have already explained under random waves. So, this Km is related to the dispersion relationship as indicated here. X and y are the coordinates, horizontal coordinates at which the surface elevation is being considered at any location x and y. Is that clear? So, this general expression provides you the description of wave elevation very clearly. It has considered the frequency components, it has considered the directional components, and it has also accommodated a particular location in as a function of location. So, this is in its generalized form the representation of wave profile. Now, the amplitude here is related to the directional spreading function. Now, how is this is the directional spreading function, how is it related? Half amplitude square will be equal to the product of directional spectrum into the delta f and delta theta. So, here again you have n ranging that is the theta from n equal to 1 to any number of components indicating the theta, that is the directional components, and f is the frequency components. Now, you look at equation 3. Equation 3, the upper limit is infinity. So, that means you have to have more number of that is the equation 3 as well as 5, it will become quite difficult to deal with from a practical point of view, as they refer to infinitely large number of wavelets. See, please recollect that random wave itself is superposition of a number of sinusoidal components. So, based on a number of sinusoidal components, you will have wave dynamicity. So, similarly here, when you want to superpose, if you have too many infinity, it is not possible. From practical point of view, it is very difficult. A more appropriate or practical approximation to them is to adopt sufficiently large number of wavelets in equation 3 and sufficiently small intervals of frequency and direction in equation 5. That is, in equation 5 smaller intervals of frequency and direction, but in equation 3 a fixed number of components. That is a better way and easier way, and from practical point of view it is quite feasible to simulate the waves close to reality. So, accordingly with this statement, equation 3 can be represented as shown here. All the variables are already defined. I cannot keep on redefining or keep on telling what are all the variables. By now you should be familiar. And now half amplitude square is also provided here. Now I can select the number of directional components as approximately 30 and number of frequency components say about 200. That should be alright for a representation, for the proper representation of the waves. How this 330, 200, these are all based on a number of calculations that has been done by Goda, and you have to refer his book for the complete description of whatever I am giving this lecture. Is that clear? So, spectral density, direction of spectrum, as I have said, is explained as mentioned here, where this is going to be the directional spreading function and S is the frequency spectrum. If the relationship equation 8 is used and then equation 7 can be written as shown here. Is that clear? So, for a given location, after all you will be interested in particular location, x and y are fixed, and hence equation 6, look at equation 6, this is equation 6 and you have x and y. Now these are fixed and hence equation 6 can further be transformed as eta at any location x and y as a summation of shown here, where this is a summation of the frequency components, the directional components are coming into picture here. Is that clear? So this is how you can describe the wave elevation at a given location, taking into the directional aspects. Any doubts? Shall I proceed? Now equation sometimes is employed in numerical simulation, not sometimes, it is mostly employed in simulation of 3D waves. In such a case, AM can be represented as shown here, already I have explained. This is how you represent amplitude as a function of spectral density, or the spectral density is nothing but half amplitude square, right. So the determination of AM by equation 15 is incorrect from viewpoint of wave variability, because that is a general equation, but when you set x and y equal to 0, then this equation 13 and 14 for a fixed location without losing its general description can be rewritten as shown here. These are the equations I am talking about. When time permits, you have to sit and derive yourself, okay. Sufficiently large number of k enables the application of central limit theorem to equation 16 and 17, stating that if n is large, the waves follow Gaussian distribution, or the wave elevation is normally distributed, it follows a normal distribution, or we say that the waves are a Gaussian process. Since epsilon suffix m comma n is uniformly distributed between 0 to 2 pi, between 0 and 2 pi as stated earlier, we have been seeing this right from the beginning, right from our random waves, 2D waves, and now Cm and Sm will have a 0 mean. The variances can automatically be proved to be as a product of frequency interval and the spectral density. In fact, we have done this for 2D waves. Please look at the lecture on 2D random waves wherein we have done this. Alternate representation of C waves. Alternate representation of C waves. So, it is well known that a Fourier series may represent a periodic signal which contains components at multiples of fundamental frequency or peak frequency or fundamental frequency f naught. In a complex form, it can be represented as shown in this equation, wherein an is nothing but these are the complex Fourier components or Fourier coefficients which are represented as shown here. If eta of t is real, then we must have a suffix minus n equal to a suffix n. Brush up your Fourier series. So, alternatively, eta of t can be represented as real part of that summation which is shown there, with an representing or equal to twice a into the Fourier coefficient an, in which a suffix 0 equal to 0 for eta to be mean 0 process. Is that clear? So, then with this background, a random C wave may be represented as infinitely small, infinitely sum of sinusoidal components traveling with different wave numbers or frequencies and directions, which can be given as the equation represented there, and this is referred to as single summation model. In the earlier case we had double summation, now we are having only single summation. Literature says that single summation is much better than double summation. You need to go through the literature. As generalization, including the shallow water conditions, when you want to include the shallow water conditions, that is the reason we bring in k, because k carries 2 pi by L and L takes care of the shallow water conditions. So, we can adopt S comma f comma theta. So, initially we had S of f, then we went into f of f comma theta, considering the theta also directional spread. Now we have brought in k also, that is to account for the shallow water situation. So, such that this into dk into df into d theta is going to give the contribution to the variance due to the component waves with wave numbers k and k plus dk, frequencies f plus f dk, okay, and theta k. And we also know that S eta of f into df is going to be summation of amplitude square. This is the basic definition which we have already seen. So, it can be rewritten if you account for all the other components that are being considered in the same form. We can bring in the other constituents like your frequency, direction as well as the wave number, and the whole thing can be represented as shown here. So hence the variance itself can be maybe now written as integration of your wave number spectra. Now the directional spectrum can be obtained from the 3-dimensional spectrum by the following equation. Now a directional wave number spectrum may be developed in a similar way, similar to what we have seen for the directional frequency spectrum, and the whole kind of relationship which we have been discussing will hold good here, and it can be represented the way we have written here. So which shows S of k into k of theta as a function of, as a summation of your wave number spectrum. Now you have brought in the wave number spectrum as well as the frequency spectrum, and you know how these two are linked. These two are linked by some kind of, as we have already seen, the dispersion relationship. But this involves, let me take group celerity. Group celerity will be nothing but df by dk into 2 pi, that is from fundamentals, and hence we can prove that your wave number spectra is, here we are talking only, we are talking about wave number spectra as a function of frequency spectra, both are directional spectra. You understand? What we have seen earlier, from this we had this as a function of, okay, only the 2D spectrum, from which we got the directional spectrum. Now what we have related right now, we have related your wave number spectrum to your directional frequency spectrum, and which is the link, the link is provided by the group celerity. And the other things are the one dimensional frequency spectrum and the one dimensional wave number spectrum can be obtained as, it is the vice versa, as I have explained here, the other way you can represent as shown here. So much we have talked about the directional spectrum, which is the fact, which are the two factors. The two factors are, one is your spectral density, spectral density or the one dimensional spectrum, and the other thing is, other parameter is your df theta, which is the directional spread. As I said earlier, similar to a number of frequency spectrum, standardized frequency spectrum, we have a number of standard directional spreading functions. So there are a number of directional spreading functions, which I am not going to go into the complete details, but all these things are listed, you can have a look, but I will touch upon a few directional spectrum, directional spread which is widely adopted. First is by Mubarak and Fan, they adopted a circular normal distribution as indicated there, all the variables are denoted there, and then you had we had the wrapped around Gaussian model by Boekman in 69, and that is given by this expression in the form of finite Fourier series expression expressed as it is most often used as shown here, but the widely spread widely used directional spread are these two. One is the cosine square theta, wherein the cosine square theta, the directional spread is given by this expression for absolute value of theta equal to less than 90 degrees or pi by 2 or equal to 0 otherwise. This is one kind of a spectral cosine square spreading function which is widely adopted. Then the other one is the directional spreading function. This is after Mitsuyasu, and this has come into existence in 75. They have proposed the same thing except that it is associated with the d naught, and they have brought in a parameter s which is called as spreading index. So the spreading index takes care of how the distribution should look like, whether it is a broad distribution, that is waves coming from a wide range of directions, or it is coming from a slightly narrower range of directions. So in order to accommodate that, they brought in what is called as spreading index. Now here theta is the azimuth measured from counterclockwise from the principal wave direction, and d naught is a constant introduced to satisfy the condition given below, that is the direction spread minus pi to pi integral summation of that equal to 1, which already we have seen in the directional spread. Now this d naught is given here. Theta minimum, what is the theta minimum to theta max, and cos to s of theta by 2 to the power minus 1. So as I said, S is a spreading index, is a parameter that relates the frequency, which will be discussed later. But then one thing is clear, if spreading index, that is if S increases, the spread decreases. If S increases, the spread decreases from this expression. Okay. So if the range of angle is theta minimum equal to minus pi and theta max is plus pi, that is the normal case. So the constant becomes something as shown here, where gamma is equal to, gamma is the gamma function and S is the spreading index. For example, if for just to have a feeling for the spreading index, by setting S equal to 10, for example, then d naught becomes so much, and then you can, and the direction of spreading function can easily be calculated. So direction spreading function is here, so that can be calculated, and this would be the kind of variation you would have for the directional spread. This is how you can indicate the spread of the energy as a function of directions. The other picture shows the cumulative representation, that is okay. So if you look at the cumulative distribution, now you can see here that it lies, most of the energy lies in this spread is lying between minus 30 and plus 30 degrees. That is where the contribution of the wave energy waves, the directions which are coming from minus 30 and 30, and that is where the majority of the contribution of energy to the total sea wave takes place. That is what it indicates. This is what is mentioned here, that it is observed that 80% of the wave energy is contained in the wave spread between minus 30 and plus 30. So this I have already explained here that about the parameter S of the directional spreading function represents the degree of directional energy concentration and has a peak value around the frequency of spectral peak. So the value S decreases towards the higher frequency and lower frequency on either side of the peak. So the spreading function of Goda and Suzuki, this came up in 1975, where they have represented this S spreading index as a function of S max, and the relationship are given here. Now this is relating the spreading index as a function of peak frequency. That was the contribution made by Goda and Suzuki in 75. And here the spectral peak is also related to T 1/3 as shown here. Now the direction spreading function as a function of dimensionless period frequency. Now let me call this as, this is f theta is frequency at which the spectral energy is maximum. So the spreading function for different values of this ratio for a particular S max is provided here. S max, say for example for 20 is fixed, then this is how the spreading function would look like for, if you assume S max equal to 20, and this shows how the energy is distributed as a function of a direction. Please remember it was Goda and Suzuki who brought the relationship between the directional spread and the peak frequency. Directional spread in terms of your spreading index, as I have explained in the previous slide, and this is how it would look like. So as your f by f naught increases, you see that you have a wide range of distribution, wide range. If it is less, you have the spreading function narrower. So if it is narrower, most of the waves are coming within a very small range of directions, that is what it indicates. So the value of S max for practical engineering applications are given here for wind waves. This is the reason why the S max was brought into picture. That is, for wind waves it is S max equal to 10, mostly that is what is used, around 10. Swell and short decay distance with relatively large wave stiffness, we use a value of 25 is recommended. Swell with long decay distance, S max is recommended as 75. So having seen in detail the representation of eta, we can use the relationship easily, the relationship between eta and the particle kinematics, and it is possible for us to obtain the expressions for the velocity particle kinematics. Earlier we used to see only for u and v, that is the two horizontal planes, one horizontal in the direction of wave propagation, one in the vertical direction. Now we have, now that you have the directional waves, so you have two horizontal in the horizontal planes and one vertical, and that is what is given here, u, v and w. So the expressions are given here, so you can use those expressions, all the values, all the variables are defined. So use this formula to simulate your particle kinematics. Is that clear? So if you have measured UV and also you know eta at a location, and if you want to really prove that your measurements are correct, use these expressions and try to validate your measurements. Is that clear? So instruments used for I will just give a small explanation about this. Usually you have a wave rider buoy. When they say wave rider buoy, that means it is not going to measure the directions. If it is installed in a particular in a location, at that particular location it will give the wave elevation record. Is that clear? So it will give only the, you can get only the 2-dimensional spectrum. But if you have a directional wave rider buoy, here it is a wave rider buoy, but in this case the direction also is measured. If you have a directional wave rider buoy, so the left hand side shows the tide gauge, and we have used all these equipments to monitor for the purpose of obtaining some detailed, for carrying out some detailed investigation on the wave and flow field conditions within a groin field. We have used some of these instruments in collaboration with NIOT. This is part of a major project. So I will just show you some recording what we have done. So this tide gauge will record for every 3 hours, it will have a measurement record of for about 35 minutes with a sampling interval of 2 Hertz, and in the other case it will be the sampling rate was adopted as 1.28 and the record length was about 1800 seconds, and herein the recording was on a continuous basis. The data was transferred online, and then we used to then take the data and for further analysis. So this is a groin field along north of Chennai Harbour. So Chennai Harbour, again some of those, so this is India map, something like, so somewhere here is Chennai. So we have a groin field wherein we wanted to work on the do some measurements. Some of the stations are located here. We had the measurement of waves and other parameters here, and this is station 2, station 3, station 4 and station 3 also is there. So then this is within a groin field. All this red color indicate the groin field, groins. So this is station 4. So the typical time histories recorded at station 3, station 4. So station 3 and station 4 are indicated here. So the black one gives you the wave elevation, the red indicates the inline velocity or the horizontal, both are horizontal, one is in the horizontal direction and in the other one blue is in the transverse direction. So with which you can also find out what is the directional spread at that location. So this is a typical surface elevation and its spectral density at this is in station 3 and 4. So this is station 3, one of the stations. So this is how it provides you the information. So what is the kind of a frequency range for which the energy is really dominant, etc. All these information can be obtained from such a result. So this is the directional spectral density, as you can see here, direction is there, while frequency is also there, and from an analysis we have obtained the wave direction, and the predominant or the principal direction is as indicated here. So this spectral density exhibits 2 peaks. This is another location wherein in station 4 how the directional spectrum looks like and its distribution of its directional spread. and the spectral density, the 2-dimensional spectral density, and also the analysis collected during Thane cyclone is reported here. So the Wave Raider boy measured all this information. So you have the raw data here, you have the 3-dimensional spectrum, how the theta is distributed, how the spectral density is looking, all this information can be obtained. This is the spectrogram, the raw data which shows the relationship between time and frequency. On the right side you see the what you see on the right side is the energy concentration as a function of frequency, and on the bottom figure you see the energy concentration as a function of time. This demonstrates that what you can do with the information on the directional waves. I think with this I will close.